Good afternoon to all of you, and I welcome you all to this session on conduction and convection heat transfer. In last classes, we discussed the one-dimensional steady-state heat conduction through plane surfaces. We also discussed the plane surface where the area is cross-sectional area, that is area normal to the heat flow is varying. How to deal with these problems, and we have solved few interesting problems in the last class. Now today we will discuss one-dimensional steady heat conduction in cylindrical geometry. Now in a plane wall, as we have seen the application where we can use the Cartesian coordinate system, but in cylindrical geometry we have to use cylindrical polar coordinate system. Now the cylindrical geometry comes mostly in case of pipe. When a hot fluid flows through a pipe, then the heat is being transferred from the fluid by convection to the inner wall of the pipe, and then by conduction from inner wall to outer wall of the pipe. And in many occasions, to reduce the heat loss, we have to provide insulating material which are solid, and provides another thickness to the cylindrical pipe. So those are the applications of steady one-dimensional heat conduction in cylindrical coordinate system. Let us see that. Let us consider a cylinder like this, and the problem is specified like this, which we will be discussing. Let this is the center, the cylinder with inside radius R1, a cylindrical tube, outside radius R2. That means this portion is the solid cylindrical wall type of thing, and the length of this cylinder is L. And the problem is like this: R2, the outside radius of the tube, outer radius, is very less than L. That means length is much more than its radius, and the inner surface is maintained at a temperature T1, constant temperature throughout the surface. Show it this way so that you can understand. So the inner surface, cylindrical surface, is maintained at R1 at T1, while the outer surface, this surface, is maintained at a temperature T2, and T1 is greater than T2. Now in this case, since it is maintained at a constant temperature, there is no variation in the azimuthal direction, theta, and also the temperature is same along the length of the cylinder. This is with respect to this can be expressed in terms of cylindrical coordinate system. If it is Cartesian coordinate, this R, this is the polar or azimuthal angle theta, and Z. So Z, R, theta and Z is the coordinate system in which any point here in the cylindrical wall R1 to R2 can be specified, where Z is the coordinates along the length, and R and theta the radial and the azimuthal coordinates. Now for this type of boundary conditions, constant temperature both azimuthally and axially along the lane, that is along z direction, and R2 being less than L, this assumes a one-dimensional heat conduction, and we consider a steady state. That means the heat is flowing in such a way that temperature is invariant with time. That is the situation when we are going to analyze the problem. Each problem in practice assumes a steady state when the boundary conditions are steady. That you have to understand. A problem becomes inherently unsteady continuously when the boundary conditions are unsteady. But if boundary conditions are steady, after a transient, a system always attains a steady state. So we consider a steady state. In this case, T is a function of R only, and only the heat flux in R direction exists. Only QR exists. That means there is a heat flux in the R direction, QR. Now our job is to find out the temperature distribution, heat flux distribution, what is the amount of heat flux across any section, all these things, which we did for plane surface. The analysis is exactly the same as we did for plane surfaces. Only difference is its mathematical shape. How we proceed with this, that we take an element, annular element at an arbitrary radius r. We take an annular element like this, a cylindrical ring at an arbitrary radius r with the thickness delta r. For clarity, I draw it here, this annular ring. This is at an arbitrary radius r with this one delta r. Then our same analysis, what we do is that if QR is the heat flux incident on this area, inner area, then this is the dimension, I am sorry. If QR is the heat and heat going out is QR plus delta R. The equation is very simple. If we consider a heat generation per unit volume Qg within this cylindrical wall, which extends from R1 to R2, then for this elemental ring, I can write QR plus delta R at steady state is QR plus Qg times the volume of this element. The volume of the element is, the cross-sectional area is twice pi r into length, where L is the length, that means it is a cylindrical ring. Length is perpendicular to the direction of the board. This is the area times delta R. That means this is the total thermal energy generation. So QR plus delta R going out is QR plus. At steady state there is no other alternative. So this is the same equation which we wrote for plane area. And I always told that, is my suggestion, that for steady one-dimensional heat conduction, it is better to derive the equation from fundamentals. This is okay. Now, if you write by Taylor series expansion, QR plus delta R is QR plus del del R of QR delta r plus higher order term which in delta r, which we neglect, higher order term in delta r, because delta r is very small. So if we write this qr plus, then we can write del del r of, I am doing slowly, qr delta r is equal to qg into twice pi r L delta r. So this equation is the same as we did for plane wall. Now we have to replace QR by Fourier heat conduction equation. What is QR? At any radius at an arbitrary location r, QR is minus k into the cross-sectional area at that r into dt dr. So therefore, if we put that here, now here also twice pi r L, actually it is the cross-sectional area. I can write in terms of the cross-sectional area AR. This is nothing but the cross-sectional area, twice pi r L, so that we can write, now this del del r I can write as ddr, because it is a one-dimensional heat conduction. QR exists and it is a function of r only. ddr of, take this here, k this side, AR dt dr plus qg AR is equal to 0. Delta r gets cancelled. My sole intention to write in this fashion, again this right to AR, though I wrote earlier twice pi r L, it is very simple, that this is the same equation which was used in the plane surface with varying area, that ddx in x y coordinate system, when t is a function of x in a Cartesian coordinate system, k ax dt dx plus, sorry, this is not qr, this is qg, qg ax 0. But the difference is that in plane area, this a may be constant under certain situation. It will come out and equation becomes ddx k dt dx plus qg is 0. And in some cases it is varying, and the integration depends upon the type of variation of a with x, even if k remains constant. But here AR is fixed. AR is 2 pi r L. AR is 2 pi r L. So therefore, if you just substitute this, then you will get ddr, and if you take 2 pi L to be constant and L cannot be 0, so you can cancel that, ddr of k r dt dr plus qg into r equals to 0. And this is our basic equation for temperature distribution in differential form. If k is constant, then k will come out, it may be going there by k. Now this same equation, I again tell you, can be derived from the general heat conduction equation. The way I told the plane surfaces also, that we can generate the same thing by, it is better always to make an energy balance for a steady one-dimensional and derive your own equation. But from the general equation also we can come to this. In a cylindrical coordinate system, the same thing will appear. Just for your interest I tell you, if you recollect the general energy equation which was derived in the class in terms of Cartesian, in a Cartesian frame of reference, rho c del t is equal to del del x of k del t del x plus, if you remember, del del y of k del t del y plus del del z of k del t del z plus qg. So this was the general energy equation where C was defined as a specific heat, which is defined in such a way that mass times the specific heat times the rate of change of temperature equals to the rate of change of internal energy of the material. Internal energy, and in a solid it is the change of the internal energy, because there is no flow, no other energy crosses the boundary. So therefore it is the change within the control volume, it is the change of the internal energy. So this is the left hand term. So therefore this equation, you know, you are familiar with general energy equation, general heat conduction equation. But now the question is that this is in a frame of Cartesian coordinate system x, y, z. How do I get the same equation in cylindrical coordinate system or cylindrical polar coordinate system? There are two ways of doing that. The most simple way of doing this, that you just transform this equation in vector form. You write this in general vector form. Del t is equal to, what is this? Del del x of k del t del x, k del t del y. This is divergence of k grad t plus qg. And you know, in Cartesian coordinate system, grad t is what? Ijk being the unit vector along x, y and z direction. I del t del x plus j del t del y plus k del t del z. And divergence is a vector operator which is I del del x plus k. This is again a recapitulation of your school level thing. Sorry, this is j plus k del del z. And if you make this scalar product with this operator and the grad t, k grad t, you get this. So if you convert this, then your job will be only to expand this term in different coordinate system, not only cylindrical, even in spherical polar coordinate system. What is the expression of divergence k grad t? Because this is only the spatial derivatives which change with respect to the coordinate system. That's all. So in a cylindrical polar coordinate system r theta z, if we write this divergence grad t, then it will be like this: rho c del t plus is equal to 1 by r, I think you know this thing, del del r of k r del t del r plus 1 by r square del del theta of k del t del theta plus del del z of k del t del z plus qg. That means in a cylindrical polar coordinate system, if we define a cylindrical polar coordinate system like this, in xy plane, if I define this a point r and its azimuthal this, and this is its location in three-dimensional, a cylindrical polar coordinate system, from the origin by the radial coordinate r, azimuthal coordinate, and the axial this z coordinate. So in that r theta z, if you expand this divergence k grad t, you get this term. That means this is the counterpart of this. And here, for one dimensional, definitely you just ignore this. And steady state, so steady state one dimensional is 1 by r. That means if you take r, this becomes the same expression. That means 1 by r. That means this equation becomes 1 by r, and del r you write ddr. That means from the general heat conduction equation we can also get the same expression, that is 1 by r ddr of kr dt dr plus qg is 0. So this is my one-dimensional steady heat conduction through a cylindrical wall. Is as simple as that. Another way of deriving this equation is the same. This is the most simple and intelligent way. Another way is deriving this equation is the same the way you derive the heat conduction equation in Cartesian coordinate system. What you did, you took an element or a control volume in the conducting medium whose surfaces are parallel to the coordinate planes, or edges are same thing, parallel to the coordinate axis, and which becomes a parallel pipette for a Cartesian coordinate system. Similarly, you have to consider an element or control volume whose planes are parallel to cylindrical polar coordinate system. That means parallel to r theta, r z, z theta plane. And then recognizing the heat flux flowing across each plane and take a balance of the total heat flux coming into the control volume with its change in energy, the way it has been done for Cartesian coordinate system. And it is a routine matter, and it is done in any book. You can see that this is not being done in the class, but most easy way is to convert this into cylindrical polar coordinate system by expanding this divergence k grad t in the respective cylindrical coordinates. Now, after this, my job becomes much more simple mathematics at the school level to integrate this equation. And before that, I consider another simple case, that k is constant. We consider that k is constant. We consider that k is constant. Now, when k is constant, this expression comes 1 by r ddr of r dt dr plus k is constant. So, if you take k plus qg by k, 0. Now, next you consider without heat generation, that means q is 0. That means without heat generation, steady state, constant thermal conductivity, the expression is 1 by r ddr r dt dr 0, which means ddr now this becomes so simple that it is a mental problem. Without paper we can solve it. The solution of this is T is equal to some constant ln r plus C2. R dt dr is C1, is constant, and then again integrate C1 T C1 ln r dr by r plus C2. Okay. What are the boundary conditions? Boundary conditions are this. At there are two constants, two boundary conditions also given in the problem. At r is equal to r1, t is equal to t1. At r is equal to r2, t is equal to. And if you use these two boundary conditions, you get a profile temperature distribution T1 minus T divided by T1 minus T2. T1 is the inner surface temperature, which is higher than T2, is equal to ln r by r1 divided by ln R2 by R1. It is very simple that you substitute this to find out C1 and C2. T is equal to T1 is C1 ln R1 plus C2 and T2 is C1 ln R2 plus T2. And you can find out C1, C2, and finally you get this as the logarithmic distribution. This is the temperature variation with R. It cannot be linear because here area is varying in a way that it is directly proportional to the R. Now if you find now the QR at any section, at any arbitrary section, that already we wrote the expression minus K into AR, that is twice pi RL into dt dr, into dt dr. What is dt dr? Dt dr is minus dt dr is minus T1 minus T2 divided by, this is constant, ln R2 by R1, and this differentiation R1 by R and again 1 by R1, that means 1 by R. And if you multiply here, that R cancels, that means QR becomes, and minus minus is plus, so therefore twice pi KL divided by ln R2 by R1 into T1 minus T2. So it is found that with this temperature distribution, heat flux at any radial location R is independent of R. Obviously, because I have found this temperature distribution from the steady state concept. Without heat generation, QR plus del R has to be equal to QR. We have made QG 0. So therefore it has to be like this, that this proves that it is okay. So this is the heat flux, and this heat flux in the similar way can be expressed as T1 minus T2 in the numerator QR divided by ln R2 by R1 divided by twice pi KL. And this acts as the conduction resistance. So therefore, if I write Q is equal to T1 minus T2 divided by conduction resistance, this conduction resistance is equal to ln R2 by R1 divided by twice pi Lk. That means this can be represented by electrical analogous circuit like this, that this is the QR radial direction, this is T1, this is T2, two potentials, T1 is greater than T2, T1 is greater than T2, and this is the R conduction, which is, in case of plane surface it was L by K, in case of cylindrical wall it is ln R2 by R1, or what nomenclature you use, R O by Ri, some outer radius to inner radius, that means ln times the ratio, that means ln of the ratio of the two radius, and then R2 by R1. These chalks are very bad, twice pi Lk. Okay. Now this thing can also be deduced in a very simpler way. How? The same thing, Q is twice pi KL, T1 minus T2 divided by ln R2 by R1 twice pi KL. I am telling you another method which you see often in a book, because this is a very generalized approach to find out the temperature distribution and like this. But another method is sometimes used, that at any radial location QR, I know the temperature distribution is like temperature. Heat flux is K into twice pi R L dt dr. there is no assumption. QR is minus K2 pi RL into D. This is a Fourier laws of heat conduction. Now, if I neglect heat generation, steady state, we did so many things, but it's a very quick approach that QR, that means across any cross section at any R is constant. That means QR itself is constant, that you can write as Q itself. That means I can write Q and I can make like this twice pi Lk equals to pi R, pi Lk equals to R dt dr. And next we can write Q by 2 pi Lk dr by R is dt. Now if I integrate this from R1 to R2, inner to outer, and the variable t, T1 to T2, and with this consideration that Q is constant, which is not varying in the radial direction, because for a steady state heat transfer without heat generation, same heat has to pass through each and every cross section. The similar way I told for plane wall also it can be done like that. So in many books it is done like that. If you integrate this, taking this out, this will be simply T2 minus T1. You straight get this equation. Q is equal to QR or simply Q, whatever you call this, you can now think of as Q. So Q is equal to that heat flux already in radial direction. There is no point of writing in the radial direction QR. Q is equal to this. Automatically you get it. Now the question comes here, by this I arrive an expression of heat transfer in terms of the terminal temperature difference. But where is the temperature distribution? Very good. Then you can take an arbitrary R, not the R2, the outer radius, and take it T. Then you get an equation Q, heat flux in terms of T1 minus T, and here it will be ln R by R1. Becomes a mental problem, and divide one by another, you get the expression like this. So this is the most easy way also to find out the temperature distribution, that you write the heat flux, connect from 1 to 2, integrate, you get the heat flux in terms of the total potential difference, or you take any arbitrary location R with a temperature T there, then you get an expression Q in terms of T1 minus the temperature T, where this will be R2, R instead of R2. And divide one by other, you can go. This is the easiest way of finding out that. But always it is better to derive an equation, because under certain special or complicated cases, you must have this practice of generating the basic equation from an energy balance over a small element of the heat conducting medium. This is always good, so that you arrive at and solve the temperature distribution and then write the Fourier heat conduction equation, get that thing. And this is one of the easiest way most of the books write, that taking Q to be constant across all sections, you get this. That's all. Now, next is similar to the plane wall, we can have a convective boundary condition. Means that this, if I draw this front view, that means in r theta plane, instead of prescribing the inner surface and outer surface temperature, we prescribe the fluid temperature, inner fluid temperature, which may be TFI, and outer fluid temperature, which may be TFO. That means the heat comes from the inner fluid to this. Let us consider TFI, fluid temperature inner, is greater than TFO. then first by convection heat will come to the inner surface and it will have a temperature T1 which is not prescribed, and then heat will flow by conduction to this outer surface which will attain some temperature T2, and from T2 by convection it will go to outside fluid TFO. For example, heat is being lost from a hot fluid flowing through the pipe. So in that case, T1, if T1 and T2 are not prescribed, only TFI, TFO, then what we can do? We know that conduction heat transfer between T1, T2, if T1 and T2 are the inner and outer surface temperatures which may not be prescribed, but I take as this temperatures is denoted as T1, T2. I already know that this is equal to ln R2 by R1 divided by 2 pi Lk, and same heat Q is coming through because of steady state, the same heat is flowing by convection from the inner hot fluid to the surface, and if I prescribe Hi as the heat transfer coefficient of the inner fluid and HO that of the outer fluid, then by our definition of the heat transfer coefficient in convection heat transfer, D can be written as heat transfer coefficient into area twice pi R1L, inner surface area, into TFI minus T1, and that is same as that goes out from the outer surface to the outer fluid environment which is taken to be cold here, less. Therefore, this will be twice pi R2L into T2 minus TF outer. So in the similar way as we did earlier, we can express this if T1, T2 Q times this, TF minus TI is Q times this, Q divided by this, and T2 minus TFO is Q divided by this, and if we sum it up, then we get Q is equal to, in terms of the extreme temperature difference which are prescribed, that is TFI minus TFO divided by 1 by 2 pi R1 H1 plus ln R2 by R3 divided by twice pi Lk R1L, twice pi R1L Hi plus 1 by twice pi R2L H2. Extremely simple. So it is the R1 and it is R2. Ln R2 by R1. I have written R. Sorry, very good. Now this is same as the flat plate thing. That means it is the sum of the three series resistance. This is convection resistance, C convection, inner surface I, this is R conduction, and this is R convection outer surface. That means extremely simple, three resistances are in parallel through which the same heat is flowing, and the electrical analogous circuit is like this, TFI and TFO. The same heat is flowing Q with, this is R convection, I whose value is 1 by 2 pi R1 L H1, and this is conduction, and this is R convection. Same thing. We can also think of composite cylinders or composite cylindrical walls which may be composed of different thermal conductivity. Then we will have the different conduction resistance in series. Different conduction resistance in series. So it will be nothing great. If we solve problems, then you will see the application of it. That means instead of one cylindrical wall, we may have a composite cylindrical wall. That means we have another cylindrical layer of material of different thermal conductivity. Then we will be adding another conduction resistance like this. That will be from R2 to R3. That means if we have another, just like this, I give you a picture like this, and this will be very simple to deduce. This will be very simple to deduce. This will be very simple to deduce like this. If we have two cylindrical walls, the radiuses are R1, R2 and R3. Then R1 to R2, this material has thermal this is A, thermal conductivity Ka, and this R2 to R3, this material is B with thermal conductivity Kb. And if we have the similar TFI and TFO with HO and HI, heat transfer coefficient, then your circuit will be the same with another added resistance, which will be very simple to conceive, and we can draw the network like this. One convective resistance, then two conduction resistance, and again a convective resistance. So that these two terminals are the extreme potentials. TFI, Q flows like this, TFI is greater than TFO, and we get this convection. What is that? 1 by twice pi R1 L HI. Then this is R conduction for material A, that is ln R2 by R1 outer to inner radius divided by twice pi L Ka. Similarly, this is R conduction B, which is ln R3 by R2 outer to inner radius of this cylindrical wall divided by twice pi L Kb, and this is finally R convection O, that is outer 1 by twice pi, this I write first, R3, the area L into HO. So this is so simple. So therefore this is the thing. That means composite cylindrical wall with convective boundary conditions are tackled like that. How do we get this distribution? We solve the temperature distribution by developing a expression from the energy balance, that is the heat balance, energy balance in the conducting medium by taking a small elemental volume, or you can start with the general heat conduction equation as I have told, then you solve it for the special case. If there is heat generation, then heat generation term has to be taken its dependence, with the spatial coordinates have to be taken. If thermal conductivity depends on temperature, then its dependence has to be taken. Then the problem becomes mathematical. That means whatever is involved is mathematics, so there is no other heat transfer concept. But one very important thing, which sometimes many books forget to tell, that for a variable area, plane area problem, if you start from the general energy, general heat conduction equation, you will be lost. you have to develop that equation by taking that I told in the last class, the energy balance, because the concept of variable area is not there, because it is integrated over a cross section to get a mean temperature effect, or the temperature being uniform but area is varying. That part will not be manifested if you straightforward take from the heat conduction equation. This is a very general mistake in student days. I tell you, a teacher always tells his experience from student days. The students always jump to the general energy equation. He finds that, okay, he makes steady state, del T 0, he makes Q 0, he makes everything 0, then you get that d square T dx square 0, T has to be linear in x. Unfortunately, a one-dimensional heat conduction, this is an approximation of course, for a varying area, T is never linear. T is never linear. It is A into dt dx which is constant. So dt dx is inversely proportional to A. That concept has to be clear. But in cylindrical coordinate system, because of the coordinate system itself, the area, it is inherent within the coordinate system that the area normal to heat flow, for example in the r direction, is varying with r, it is directly proportional with r. So therefore, from the general heat conduction equation, if you take the special form, it will be same as you deduce by taking a simple element one-dimensional QR and QR plus del R like that. Both the things are same. I think for you people, these two things have to be kept in mind, otherwise you will be in trouble. That even in variable area, you will draw a linear temperature profile, then come to the teacher and tell why in a steady state one-dimensional constant thermal conductivity temperature is linear, why I have not got the mark. So this is very important. Okay. So today I will stop here. Well, it is little before the time, but the next thing is the critical thickness of insulation. That I will take in the next class. Now I tell you, just wait, I give you a clue now before starting the next topic, that when this heat flux is given by this, one thing you see that if you increase the outer radius, then two things happen in contrasting nature. We increase the outer radius, the conduction resistance increases, but the convection resistance decreases. This is because surface area of heat transfer increases. You understand? Which is not the case for a plane area. If there is a heat transfer from a wall, if you go on adding material to increase the wall thickness in the direction of heat flow, you are sure that you are putting more conduction resistance and the heat flux will be arrested. That means it will be reduced, obviously, because your dt dx is getting reduced. But in a cylindrical geometry, if you increase the area, increase the radius by more material, that means you are increasing the radial path for conduction, and conduction resistance increase. But at the same time, mathematically you see the convection resistance decreases, means the surface area from which the convection heat transfer takes place increases, and convection is directly proportional to surface area. You understand me? So therefore, the two counteracting things results in a very interesting problem as critical thickness of insulation. That means if you insulate a cylindrical pipe by giving insulating material, adding insulating materials whose thermal conductivity is relatively much lower than the common conducting material, does not always mean that we are going to reduce the heat loss. Ironically, you will see that you are increasing the heat loss, because there are two contradicting things. Conduction resistance increased, but the convection resistance decreased. Clear? So with this clue, next class I will tell you the critical thickness of insulation and the expression for heat transfer in cylindrical wall with heat generation.